What is knot theory? You might think this is knot theory, but actually, it's not. There's an entire branch of math devoted to knots. They aim to identify every single knot that could ever exist. Currently, there is roughly 350,000 knots that we have discovered. Well, you might know a knot as this or this, but in the study of knot theory, you want to be able to pull them apart and see how they're tied together. This is why knots exist in closed loops. The easiest knot is the on knot, which is simply a circle. After the on knot is the next simplest knot known, the trifoil. To prove that it's a different knot, it cannot be made back into another. For example, I can't pull the trifoil in a way where it would be an on knot, but it can be quite tricky to tell. If you look at these knots here, which knot is the on knot, which knot is the trifoil, and which knot is the more complicated knot? Well, you might think this is the more complicated knot, but actually, it's just a trifoil knot. And this knot here, well, this is actually the trifoil knot. And this knot here, well, this is actually the on knot. See, this is where our problem begins. You can't just tie up some rope and make it appear like a new knot. You need to prove it. This is where our knot equivalence comes into play.
In Alan Turing's final publication, Solvable and Unsolvable Problems, he wrote, "No systematic method is yet known by which one can tell whether two knots are the same." Knot theory was slowly expanding with Kelvin Tate in Germany, discovering everything from a 3-crossing knot to an 8-crossing knot and linking it back to chemistry, making a periodic table of knots for every element, declaring that atoms must be made out of vortex rings of ether, an invisible everywhere medium. He was later disappointed with his idea when it was proven false by J.J. Thomson's discovery of the atom, which didn't look like what Kelvin had imagined. However, he had started an amazing discovery and couldn't stop, calling 2 mathematicians, Thomas Kirkman and Charles Little, for helping on extending the list of possible knots up to 11. Together by hand, the 3 of them were able to find all 21 8-crossing knots, all 49 9-crossing knots, and 166 10-crossing knots by 1899, just 2 years before Tate's death.
However, little progress was done on the knot equivalence problem until 1927, when mathematician Kurt Reitermeister proved the theorem that you only need 3 types of moves to transform any 2 identical knots into each other. That being the poke, the twist, and the slide. Although some knots were discovered to be identical, we still don't know how to tell them apart, since you could technically do the same Reitermeister moves on one knot forever without it ever appearing to look like the other knot. And maybe it is different, but maybe it's the same. And perhaps you just didn't do the right move at the right time. When Turing decided that the knot equivalence problem was unsolvable. But in 1961, a computer algorithm designed by mathematician Wolfgang Haken finally solved the knot equivalence problem, with the computer algorithm using Reimister moves, checking all possible sequences of Reimister moves, although doing this was almost impossible. As of the day, the bounty moves is 236n to the power of 11. That's more than the number of stars in our observable universe. In 2011, mathematicians found an upper bound on the number of Reimister moves, thus solving the entire knot equivalence problem. The upper bound is this: raise 2 to the power of 2, and then raise that to the power of 2 again, and then raise that to the power of 2 again. And keep on doing that over and over and over again. This operation is known as titration. Now, continue raising 2 to itself about 10 to the million n times, and then cap it off with n. How can these people tell the difference between knots? This is when we need to look closer at things that never change. These are known as invariants. Many things have been identified as invariants. To put it briefly, knot crossing numbers which measure the least number of crossings a knot can have, thus the reduced form. For example, this is a crossing, this is a crossing, and this is a crossing. Therefore, the trifoil knot has 3 crossings. Another invariant is tricolorability, which is whether a knot can be colored into 3 different colors. At intersecting lines, it must be the same color or all different colors. It works well because no matter what Rhinomeister move you do, it will retain its color. Polynomials are also used. They work by looking at the 3 possible crossings of a single crossing knot: forward, backward, and separate. All these invariants work together to identify the differences of knots. However, it isn't perfect. For over 75 years, trait knot tables listed 2 same knots right next to each other. It wasn't until years later when Kenneth Perko, a lawyer who studied knot theory, spotted them in 1973.
Knot theory can be used in the real world too. In 1989, chemist Jean-Pierre Sauvage tied molecules around copper ions to form the first ever synthetic knotted molecule. If you want to give a molecule a new property, you could tie any molecule into a knot to change its properties, meaning that you could create hundreds of millions of different materials. Knot theory can also be used in biology. Look at this bacterial DNA. You'll notice it's a knotted link. We can target these knots to kill cancer cells. These knots are known to occur around parts of the genetic code which is important for tumor cells to continue growing and dividing. By stabilizing the knots, the tumor may not be able to continue growing and the cancer could be successfully treated.
Although knot theory has started as a failed theory in the field of math, in recent years it has reclaimed its original potential. Knot theory is everything, from a simple trifoil knot to the future of chemotherapy treatment. Thanks for watching.